Hello everyone. This is Blazej Kubiak. My name is Krzysztof Kudrynski, and this is a drone. It is in the box, and the world consists of two groups of people. People from the first group will immediately take the drone out and start to enjoy flying, while people from the second group will immediately download the API. Maybe even make their own better one. Now, there is absolutely no shame to be part of the first group. I have real friends that would do this, and they are nice people. Myself and Blazej, we are proud to represent the elite. After over 2 years of experience with the drone, we have absolutely no idea how to fly that thing. So a few words about us. Between 9 and 5 p.m., we work on extremely exciting project in TomTom in Łódź, where the main idea is to enable cars to drive by themselves. And our main contribution here is turning a set of images and a point cloud of lasers into a consistent, three-dimensional representation of roads available globally. After work, we spend our time with families, Blazej with Blazej's, myself with mine. And then when normal people start to think about meeting friends and going to sleep, we dive into the world of technologies. And we have similar interests: computer vision, robotics, virtual reality, and artificial intelligence. Around midnight, Blazej walks to sleep, and I sleep to walk. This project is driven by passion. It was created during time instead of meeting friends and instead of sleeping. And in this project, the drone will learn to fly. And it will learn that skill based on what it sees. And it will see the world using a camera. So the starting point of our project is a calibration chessboard. So we can make a lot of photos of that and then use simple mathematical algorithms to find the model of distortions and remove them from your camera. In fact, almost every project in computer vision starts with calibration chessboard, and then you can practice with detecting chessboard on the screen and then tracking chessboard in the video. These are the hello words of computer vision. However, if you are here to see the hello word example, you might be a little bit disappointed. We cannot disagree that detecting chessboard and tracking chessboard have great applications, so useful in real life, ranging from detecting of freaks still playing chess on the chessboard, up to detection of people walking on the street with a chessboard. And the list does not end here. However, our inspiration is a bit different. What you can see here are the fragments of videos from the web of drones racing. It's amazing to feel that speed. And when you realize that these drones were actually controlled manually, there is one word that is screaming in your heads, I'm sure, and it is irresponsibility. Let's analyze one case. This is a frame taken by drone during some race. And the task here is simple. What control needs to be applied to fly safely? And there's a lot of time to apply that control, to think about it. There's so many frames. But if you are starting to worry, you are doing the right thing, because although there is still hope we can make it, you know exactly how it's going to end. If you analyze this case again, you will see there was so much time to react. Similarly to many other cases which ended in a silly crash while there were tens of frames ready to extract the proper information, tens of frames begging for salvation. Together with Blazej, we decided to put an end to that. The user should only click when they want to fly, and it is the machine that should calculate proper low-level controls to safely fly towards that place. And today, we will all have a walk through all the steps you need to consider while implementing that on the machine, and we will show you our examples how we did that. We will show you our tests, not from the ruins like that, not from the forests and parking lots, but from our modern TomTom office, built and opened this year. But if you look at this carefully, you cannot miss the similarity, especially if you look at the right perspective. We have absolutely no doubt that this building was built and meant to be our training ground. So let's talk about our solution. And for our inspiration, let's again analyze this simple image. We all have to agree that we humans are amazing. Everyone here immediately and without any effort is able to spot and track a safe place we're flying to. Everyone here immediately and without any effort is able to intuitively plan your next actions. Everyone here immediately and without any effort is able to understand the environment, spot the collisions, and act accordingly. What is even more amazing, this is already amazing, but what is even more amazing is that at the exact same moment, using exactly same brain, we humans are able to plan our next meal and perform deep considerations about life. But general intelligence, like that, is not yet possible according to the science, so we will not talk how to teach the drone to cook or understand life, but we will think how we humans would analyze these three tasks and how to implement it on a machine. And because the machine can be perfectly focused and absolutely dedicated to these three tasks, then by just adding enough processing power, we will quickly outperform humans. So these three steps will be the plan of our presentation and the plan of the development of our system. So let's start from the beginning. In order to start the project, you can use whatever equipment you want as long as you can control it from your software. We started with Parrot Air Drone 2, with which you can communicate over Wi-Fi, and there is plenty of open source available in the web for that. We used open source Java framework called Yadron. It's under Apache 2 license, and from the hundreds, thousands of lines of code from Yadron in this project, we used one, the move command. In move command, you need to say what tilt needs to be applied to accelerate the drone, and then ascension and rotation speed. And these three parameters will be derived directly from the image, which, for convenience, will be decoded using a C++ FFmpeg, be it either from the internal camera of the drone or the external GoPro, for example. And then this decoded image we will analyze using Python libraries like OpenCV or NumPy, and everything will be orchestrated in the beginning, that was the plan, in Java. So this simple architecture, this simple design is a starting point, and you will see it evolving while our new ideas approach and while we are developing the system. But you can think this is a nice start to start think about the logic. And the first thing in the logic is the first level of autonomy which we want to apply, which is tracking. And because we are fans of human brain, we would like to think how we humans would analyze this task. And a nice example would be when we go to the club full of people and we find something catchy, something that catches our attention. For example, a hat. But for a start, let's imagine something more familiar. Imagine that, but you must imagine it really hard. Imagine that instead of the hat, we have a chessboard. Now, this does not happen really often, but if it was the case, we would have a nice algorithm ready to accomplish our task. However, sometimes it happens that you have to track something else. And it is this particular moment, because you don't know what you are going to track, you know it when you see it. And this is at this particular moment that this defined region gains some description. It might be the distribution of colors inside, it might be the shape of the hat itself, or we may be directly tracking the flow of pixels in the image. And all of these approaches can be easily implemented on the machine, and the good news is that you don't need to do it on your own because somebody else already implemented that, and it is available, for example, in the library called OpenCV. So in OpenCV, we used min-shift algorithm. So min-shift algorithm is just, in simplification, it establishes distribution of color inside a given region and then shifts and scales that region to keep this distribution of colors constant. Cam-shift is very similar, but it also is able to apply rotation. And then optical flow measures locally the motion of pixels around the specified object. From these algorithms, optical flow for us gave the best results, so let's see how it works in our case. So what you can see here is our graphical user interface. So this is the frame seen by the drone in our office. And you can see the automatic controls applied to it. So the buttons on the sides will show what tilt, the arrows on the bottom shows what tilt needs to be applied from the left and right. Arrow on the bottom shows how high it needs to be changed in order to make that. And then this will be, in this moment, it will be all 0 because we are not yet avoiding obstacles in this level of autonomy. So let's focus on the circle in the middle, which is what it will be tracked. In the beginning, it is in the middle, but when we start flying, we will click on the table on the left, and this small table will be tracked. And finally, the arrow on the top shows what rotation needs to be applied for the drone in order to be focusing on the place where it tracks. So when we finally start flying, you see the optical flow tracking the table, and you see a strong desire of the drone to turn left. And this desire will be turned into action when we, in our graphical user interface, start press number 1, which is autonomy level 1. So orienting ourselves versus the object. And this is what happened. And now the drone is floating freely and tracking and orienting itself versus the object. So this is the first level of autonomy. We have that. In the second level of autonomy, there is not much to talk about because we will calculate the rotation, apply it so that we are orienting ourselves versus this place, and then we add some forward motion to actually fly toward that place. We did some tests. The results were expected. Without collision avoidance, you cannot do too much. So this is how we arrive at the third level of autonomy, which is where the fun begins. Because in order to avoid risks, we need to understand the spatial content of the image. And having just the two-dimensional image, this is quite hard. So again, let's think how we humans would do it. And the first answer that comes into our head is probably through the pair of our eyes. So let this diagram be a simplified viewing system. The blue rectangle is the place where the image is formed, for example, the retina of our eye, and then the dashed line is just its principal axis. And a single pixel on this image tells us very limited information about what we are looking at. To be more precise, it tells us the ray on which this object in the world lies, but we don't know how far it is until we have another eye, which is quite common. And in this eye, we find the corresponding pixel, and then using some mathematical tricks, our brain knows exactly where exactly we are looking at. And we can also implement that on a machine. So is stereo vision an answer? It might be. It might be, but then we would need to take out our monocamera and replace it with a stereo vision system, much heavier and probably much more expensive. So before we all go out shopping, let's think, let's ask ourselves a question: is it really necessary? Are we human hopeless if we have one eye only? Obviously not, because when we move, our brain is fed by multiple images, and we remember these images. And it can be mathematically proven that if in between these two corresponding images we find 7 corresponding points in general non-critical configuration, we are able to find our movement and also reconstruct the three-dimensional structure which we are looking at. Our brain does that, and also we can write an algorithm to do this. This will be a video of my chair. And in each frame, the algorithm will find characteristic points and corresponding characteristic points in the next frame, and from that, it will build the 3D structure. So you can see it on the right. And this approach is known under many names. It can be, it is structure from motion, multiple view reconstruction, visual SLAM. You can use OpenCV library to have some basic reconstruction. You can find nice projects in the web, or you can read nice book, great books about this topic, and write your own better code. And if you do it right, it works just perfect, especially if you move horizontally versus the object which you are trying to reconstruct. But if you are moving towards the object, you might have a problem, because moving towards such movement brings very little additional projective information. In fact, this information is so small, it can be confused with the error that you have from your sensor, from miscalibration. And then you may think that your three-dimensional world is flat, which is not true. It is even worse if we rotate, because if we rotate, then this movement provides zero additional information because all the rays meet at the focal point anyway. So this is quite unfortunate, because in our solution, in our problem, in our project, the drone usually flies towards and rotates until it meets an obstacle. So this is the worst case. So however cool this methodology might seem, this is not the technology of our dreams. Another similar approach would be to use optical flow itself. If you focus yourself on the door handle and the glass, while moving, you will see that the door handle moves much slower on this image than the glass because of the perspective. And you can use that in order to get the three-dimensional space again. But again here, in order to make that happen, similarly to the previous example, side motion needs to be dominant in your movement. So the first thing that comes into our head, so while we fly, we can deliberately add a little bit of slaloming motion, a little bit of side motion. And for us Polish people and our friends in Russia, adding a little bit of slaloming path would be perfectly excused. But we would not win the race that way. So are we doomed to fail? Absolutely not. And again, we will draw inspiration from the power of the human brain. Because we humans do not need two eyes to understand the world around us. We do not even need to move around. We can stand still in one place with only one eye and still have absolutely no doubt what's around us. So how do we know this? From experience. From billions of images fed into our brain, we learned how to understand objects, their relative sizes, their arrangements, and their shadows. With this lifetime experience of looking at the world, we humans need absolutely no tricks to understand the space. And as amazing as it might sound, thanks to the recent advancements in artificial intelligence, we can share this experience with the machine. So we will teach our drone, our machine, to understand the space using deep convolutional neural network. In a minute, Blazej will tell you more details about deep convolutional neural networks, but if there is anyone here absolutely unfamiliar with the concept of machine learning, the main idea is that instead of providing a set of nice rules, algorithms, and formulas to detect some object, we design a mathematical model which will take all the input, for example, all the pixels in this example, and create output label. And to make this output label correct, we will flood this model from the backwards with examples with known label. And then this model will adapt itself so that its reactions to pixels and the combinations of these reactions and combinations of combinations and so on will finally give the label which we are teaching this model to get. You can read a lot about AI, but today we want to suggest something much better. You will all be part of an amazing experiment. In this experiment, you will be the AI, and I will teach you how to perform a simple categorization task. As every network, in the beginning, you have absolutely no idea what you will be learning. And I will give you examples with labels, one by one, and your brain will shape what the categorization task is, and hopefully, finally, when I give you the nice final example, the test, you will know the label. Are you ready for training? Okay, let's start. Image number 1, label. Image number 2, label. Image number 3, label. Image number 4, label. The training time is over, and now it's time for a final test. This is a question for 1 million. And the allowed answers are yes and no. So please, raise your hands who votes for yes. Thank you. Now please raise your hands who votes for no. Thank you very much. The results are 5,035 for yes and 1 for no. Ladies and gentlemen, this is a correct answer. We have just successfully detected a sofa. Thank you very much for your participation. It was really important for me. I'm very happy we managed to be the winners today. But there is, however, something disturbing. There is this one guy who was blinded by some other less important features also available in these images. And this is a threat. If there were more animal lovers in this room, we would all miserably fail at detecting a lovely sofa. And seriously, this is a threat in artificial intelligence, because formulating a nice, well-formed, unambiguous training set is an art. And you will never know exactly what the network learned. So you usually need crazy amount of training data to make that. And as a designer, you have to decide if you can afford getting so much training data, because maybe it is possible that using only one example with your own intuition, you can design a set of rules and create your own handcrafted algorithm to make that task possible at a lower cost. In our case, finding a handcrafted algorithm would be a pain, because our task is, from having a two-dimensional image, find a third dimension, a depth map of it. Here it is shown as a depth map where the black is near and white is far. And if we have this for every incoming frame, it would be possible to spot the black places, and these would be the obstacles, and apply proper control to avoid them. It would be nice if we have that. And we will train our deep convolutional neural network to perform this task for us. But of course, in order to train that, we need training data. In other words, if we want our machine to get a depth map for every frame, we first need to give 100,000 of examples of this job done right. So how to do it? The first way would be to take a ruler, and for every pixel in this image, measure the distance between the camera and the place in the real world. Repeat that for every pixel. We have the depth map, and then repeat this for 100,000 of examples. Our rough estimate for that would be 300 years, so we decided to use a different approach. We will be using our structure from motion algorithm. Without any stress in the beginning, we can do whatever movement we want, so we will be moving sideways to create our ground truth, and then we will move towards and backwards from some object, for example, a pillar, hence the name deep pillar learning. And we will be moving precisely according to a well-defined scenario between 0 and 4 meters from the pillar, all the time the same. And this is how we would get a nice depth map for that, but this depth map, because it is structured from motion algorithm, we don't know what's the scale of that. It is a random scale, it is floating, and in order to fix the scale, we will find the histogram of the depths in time, locate the pillar inside, and then normalize this to lie between 0 and 4 meters. And then apply this normalization back to our images, hence having a nice ground truth in the metric world. And only train our network. To be honest, we are in love of our solution. But you have to know there are two solutions which would bring you faster to your aim. And the first would be to use internet. You download the ground truth prepared by someone else and then train your model. And the second would be to use internet and download the already trained network. So now Blazej will tell you more about the deep neural networks and our architecture, and I will finally tell you how our example works.
Hi everyone. Sorry for my voice. This shows just that we really enjoyed DevOps and it was nice yesterday. But to the topic. It is a great thing to make great things from scratch. However, it is a bit wiser sometimes to use existing solution, especially if it fits really well to your needs. Or you're preparing a great demo for DevOps and you have limited time. So we use deep neural network for dev estimation. And we find it in the internet. And what was very nice, not only the network structure, but also pre-trained model was available to download from the GitHub. It was available in the format. We used second one for TensorFlow. What was really nice, authors also prepared some Python script. If you read it, you can really check how to play with the network, how to load the model, feed the network with your custom data. It's very simple. So it is very nice. And now we could just use that stuff, but we really like to know details under the hood. And we also like to share it with you. Okay, there is one thing. When we download all the stuff and we did first test with our data, we were a bit scared because the model size was around 200 megabytes. It was loading in 5 minutes, and dev estimation took around 30 seconds. So it was far away from real-time performance. But fortunately, in our office, under my desk, there is a very powerful machine with 2 NVIDIA GTX Titan X cards, and on that machine, we could perform it with 100 milliseconds, which was very nice. So let's go to the details. So solution can be described in just one sentence. deep, fully convolutional neural network with upscaling layers, fine-tuned from residual network 50. It is a bit terrible, so I will try to translate it to human language. So let's start with neural network. So probably everyone has seen such image. It is just classical, fully connected neural network where a neuron at any layer is connected to all of neurons in previous layer. There are connections are weighted. During the training process, we are changing weights to make the network correct predictions. So why can we use our drone, take the photo, and just fit such a network with image, with just image pixels? So imagine how many weights would you have in that network. So we have 100 by 100 pixels and 3 channels. And in next layer we have neurons are connected to every neuron in previous layer. We have 3 hidden layers, so we end up with almost billion of weights. So it will be very difficult to train such network. It will be so many degrees of freedom that network couldn't converge to the solution. That's why we need to switch to convolutional neural network, and I will tell you how it is better, why it is better. So it bases on operation called convolution. This operation takes the frame on the left and the kernel, sometimes called filter, on the right, and it just it calculates product values between pixels in frame and in the kernel and adds them together and put in output image. It will be easier to understand on the video, so iterating over pixel, and for each 9 pixels we convolve it with the kernel and place the output in the output image. It's quite simple. Next operation that is used in convolutional networks is max pooling. It is used for downscaling image, but it should also save all necessary information that will be used for further layers for feature extraction and classification. So it basically, for each 4 pixels, it just takes maximum value and put it in the output image. So operation is very simple, but it works very well. And last operation important is unpooling, because it is for upscaling. Because we don't know what to put in every pixel in upscaled image, we just put the values from input image in left corner for each 4 pixels in output image. It looks maybe that it shouldn't work, but it's very useful. Activation function. In convolutional networks, we use rectified linear unit. It is basically a linear function, but for negative values, they are saturated to 0. This function was introduced in 2000, and it is biologically motivated. So scientists think that our brains works in this way. So let's see how convolutional layer looks like. So we have 3 channel image, for example. We have 3 kernels, so there is also a separate kernel for each channel. We perform convolution, sum together, apply activation function, and we have feature map. If you would like to have multiple feature maps, we need to use multiple set of kernels. Now I think this is most important slide. I will compare what is difference between convolutional layer and fully connected layer. I think this thing is skipped in most presentation, and it is most important, in fact. So when we count the number of weights in first layer, we have 3 channels, 3 by 3. It is only 27 weights. If we would like to have, for example, 100 of feature maps, you would have 2,700 700 weights. On the other hand, on a fully connected layer, we will have around 300 million weights. And we produce only one output, let's say. So convolutional layer may be treated as feature extractor, because with very limited number of weights, it produces huge number of features, huge output. And on the other hand, fully connected layer, it uses many weights, but it aggregates features. And this aggregation nature of fully connected layer is used in classification. Okay. There's also one more thing, which is let's call it attention to the structure or local structure. So in a fully connected layer, because every pixel in output is connected to every pixel in input, the network may think that appearance of the rubbish bin may be somehow related to, for example, appearance of flower. It's crazy. In the convolutional layer, all features are really local, maybe in some local, small local context. Sometimes context may be a bit bigger, but it's still local. And this is huge difference. This is typical picture of convolutional linear network. There are a few convolutions and poolings, which is the feature extraction part, and a few fully connected layers, which is classification part. These days, it's quite popular to remove classification part completely, exchanging it with another convolutions and poolings. And with that network, it's called fully convolutional layer. And at the end of the network, there is just one pixel that gives you the value, which is the output of your network. So we cannot use that network for our task, because for the image, we would have just one depth prediction, but we would like to have depth prediction for every pixel in input image. That's why we need upscaling layers. So we are adding some upscaling layers, which are basically convolutions interleaved with unpooling, and we have full resolution depth map. Fine-tuning. It is quite difficult to train the full deep network from scratch. That's why many people uses pre-trained network, just cut off some layers, adding another layers, and train the network again for another task. And authors of this network use this approach. So they took residual network 50. They cut off classification part, they added upscaling layers, and they trained it, network previously trained for classification, anything like bicycles, cats, and everything. They trained it again for depth estimation. And the results are very nice. So in the middle, we see ground truth, which is basically labeled data set. And on the right, we see depth predictions, which looks very nice for me. So now we will, Krzysztof, continue.
Okay, let's come back for a while to our initial system design, which is already a little bit complicated with the components for convenience written in different languages. And now, when we add our deep neural network prediction, it becomes even worse. Because not only we face porting everything to a Linux machine with a CUDA support, but also we cannot just call Python scripts independently every time a frame comes, because this would kill us if we do this every time. Of course, obviously, it is solvable, and there are people capable to manage all the possible pieces and make them work together as a perfect unity. But for those who cannot, the world brings microservices. Yes, this was a joke, a good one. For those of you not laughing, this is not microservices according to the definition probably, but breaking our design into client-server components made our life much easier. Now the headquarters is the Python application which communicates with a FFmpeg service to get the decoded image. Then it uses the CUDA service to which, when given a frame, will return a depth map. In the Python application, we have a graphical user interface where we can apply commands manually, but also here we can press 1, 2, 3 to give autonomous level to the drone, and it will fly by itself. And then based on that, depending on that, the control server will serve automatic or manual commands to the client, which communicates directly to the drone. So, having all the puzzles solved and explained, it is time to show you our ultimate demonstration, and we are very happy to be able to show this video to you, because during the day of recording, we had a fire. If you don't know what a fire is a set of failures that every self-respecting developer should experience during the day of delivery. Now, you will not see these problems on our video because we have a perfectly stable delivery platform statistically proven to be PowerPoint, so you can watch it without any frills. Okay, but seriously, our results were quite nice. Everything works smoothly. We only had some problems with the communication with the drone, so frankly speaking, this is the best out of 10 videos probably, and others are impossible to watch. So let's watch this one. So on the right, you see our drone flying, but what's more interesting is on the left, the applied automatic control. You can see that. So in the bottom, you can see the output from the deep neural network, and when it turns deep blue, we find this region and we apply proper automatic level control. So everything is done automatically. The only thing we done in the beginning, we showed where we want to fly, which is shown by the circle. So the red circles tracks the window for which we fearlessly fly towards without any other manual control to the drone. Because this is the best and the only video that we have, I will play it again so that you can watch it in peace. So according to the task defined in the beginning of this presentation, the user only selects the place where they want to fly, and it is the machine that understands, that learned to understand the three-dimensional content of the world around it through the two-dimensional picture. And it flies on its own, which is the conclusion of our today's lecture. But before we finish, we were joking a little bit, and if we offended anyone while we tried to be funny, please accept the following rectifications. First of all, dogs are more lovely than sofas. Second, not all chess players are freaks. In fact, if you have a nice traditional chessboard, chess can still be a nice game. And finally, irresponsibility is fun. There are only two rules to remember. In your office, please watch out for the lamps. And the second one, if you happen to record a video on which your drone flies and crashes into the workspace of your boss, never show it to the public. Thank you very much.